Alright, so in this video I'm gonna be explaining another important paper with the title Large Graph Property Prediction via Graph Segment Training. This NeurIPS paper in 2023. Learning to predict properties of a large graph is challenging because each prediction requires a knowledge of an entire graph, while the amount of memory available during training is bounded. Here we propose graph segment training, a general framework that utilizes a divide and conquer approach to allow learning large graph property prediction with a constant memory footprint. GSD first divides a large graph into segments and then backpropagates through only a few segments sampled per training iteration. We refine the GSD paradigm by introducing a historical embedding table to efficiently obtain embedding for segments not sampled for backpropagation. You see the full graph training. Classically, models are trained using the entire graph, meaning all nodes and edges are used to compute the gradients. For large graphs, this might be computationally infeasible. So now you see in figure B that it is a graph segment training, that our solution is to partition each large graph into smaller segments and select a random subset of segments to update the model embedding for the remaining segments are produced without saving their intermediate activations. Because we want to accelerate the training process further, we introduce a historical embedding table to efficiently produce embeddings for graph segments that do not require gradients, as historical embeddings eliminate additional computation on such segments. So we define an embedding table tau where a key space is a tuple. So this is our method, the method of this paper. Given a training graph dataset, a common SGD update step requires calculating the gradient, where theta is just the weights in f prime OF, and this is a sample mini batch B. Graphs can differ in size, with some being too large to fit into device memory. This is because the memory required to store all the intermediate activations is proportional to the number of nodes and edges in the graph. So to address this limitation, we propose to partition each original input graph into a collection of graph segments. So this pre-processing step will result in a training set, and the number of partitions can vary across graphs. When processing graph segments, we can obtain its segments embedding through the backbone. Now, the naive applying prediction head f prime on aggregated graph embedding is this. This would not provide any reduction in peak memory consumption, as we need to keep track of activations of all graph segments to perform backpropagation. Thus, we propose to perform backpropagation on only a few randomly sampled graph segments and generate embeddings without requiring gradients for the rest. We hereby denote H sub S and H sub J as segment embeddings that require and do not require gradient, respectively. And entire graph embedding is then, this is the entire graph embedding. So to summarize, we first sample the mini batch, we sample graph segments, we produce embeddings, and then we do SGD on the loss. So let's compare the input-output distribution of the prediction head f prime during the training and inference stage. We have training distribution and test distribution. Regardless of the innate distribution shift between training and test stage of the dataset, we note that stale historical embeddings can further widen the gap between training and test. So in this case, the minimizer of the expected training loss does not minimize the expected test loss. So to mitigate this distribution misalignment, we introduce this the prediction head fine-tuning technique. So at the end of the training, we update each embedding in the embedding table tau by forwarding each graph segment in the training set with the most current feature encoder F. The fine-tuning technique addresses the negative impact of stale embedding on prediction head F prime. However, the staleness also impacts the backbone. Prior work studying the effects of stale historical embeddings commonly assume that historical embeddings do not become too stale. So this staleness introduces an additional source of bias and variance to stochastic optimization. We assume that we keep the probability P, the weight eta for each segment is defined like this. So we denote our final algorithm GST-EFT, which we summarize in algorithm 2. They did some tests on the data sets like MalNet Tiny, MalNet Large, with different backbones like GraphSage, GCN, and GraphGPS.